Alright YouTube, what's going on? It's Rewire Strike. So today I'm going to be talking about, or in this video I'm going to be talking about well-posed boundary value problems for partial differential equations. A boundary value problem is well posed if 1. L is linear, I'm going to go over that. 2. L is inverse monotone, I'm going to go over that as well. And 3. We introduce a function phi that is bounded and non-negative function of x, such that phi of x is greater than or equal to 1. Alright, so to start off, I'll cover the first one, linearity. So, linearity properties of L, similar to a previous video that I did over classification of PDEs, the linear rule states that if a linear operator L over addition of u plus v is equal to L of u plus L of v, and also that L of alpha of u is equal to L of alpha of L of u. The same conditions apply for the boundary operator v. So I'm going to go over a proof over linearity, which we're going to use later on. So we're going to say that L of u is equal to negative u double prime. Now we got to introduce L of v, which is going to be equal to negative v double prime. So we can kind of knock out two birds with one stone. We could say that L of u plus v is equal to L of negative u minus v double prime, which is equal to L of negative u double prime plus L of negative v double prime. Oh, I skipped a step. Whoops. Double prime plus negative v double prime, which then goes to L of negative u double prime plus L of negative v double prime. And that checks out this one. Now to finalize it, I'll do the alpha. Say that alpha is equal to negative 1. This implies that we get negative L of u double prime minus L of v double prime. So that checks out both the linearity. Now this is a theoretical approach to this, so we're gonna stick with this because it's gonna come in matter. This is gonna be the left-hand side of our equation in just a moment. So I'm gonna go back up, and now we're gonna talk about inverse monotone. So we'll start with monotone, and it's hard to prove. This is a little bit difficult to grasp, but if you understand the term monotonic, which is basically another way of classifying a function as monotone, you could say that a function would be monotonically decreasing if for a pair of points x naught, and f of x naught is less than I'm going to spread it over here such that a pair of points x naught is less than f of x naught is less than the pair of points x1 f of x1 for all x that exists within the bounds of x naught and x1. Okay, and that's for decreasing. And increasing is that x naught, is greater than. Dang it, I messed it up. Alright, so decreasing means that for this point here, it is greater than this point here for all of x. So for increasing, right, we have x naught and f of x naught, this pair of points, is going to be less than x1 f of x1, right? So it's increasing. And this is going to be, once again, for all of x that exists between x naught. x0 and x1. Alright, so now that we talked about that, now we're going to talk about inverses. So basic algebra that you learn is that if x is equal to f of x, and if the inverse function exists, meaning it's bijective, which means 1 to 1, the range is equal to codomain, the composition f with f inverse of x is equal to x. So this is a simple example right here. If x is equal to y over 3, I can rearrange it to y is equal to 3 of x. Now this implies two things, that the first one, y over 3 is equal to f of x, and 3x is equal to f inverse, and when I compose it, just put that in there, put 3x into the y, that becomes x. So that checks out. Alright, so that's just a recap of inverses and monotonic functions. So now, in order to now we're at our actual problem. We're supposed to prove that the boundary value problem is well posed, meaning 1, L is linear. I already wrote it. I'm going to go back up. Meaning 1, that L is linear. 2, L is inverse monotone. And 3, L of phi is greater than or equal to 1. And phi is a bounded and non-negative function of x. Okay, which is kind of an arbitrary one that we just make up. But it has to be suitable for our problem. So here's our boundary value problem. We have negative u double prime equals f of x. Now I already proved that this is linear, right? In this video I just proved that negative u double prime is linear. And we have two boundary conditions. U of 0 is equal to alpha, and u of 1 is equal to beta. Now we're going to say that alpha is equal to 2 and beta is equal to 3, and f of x is equal to sine x. Now by definition, this is kind of already putting it together, right? But in order to clarify and help you see what it is that we're doing, I'm going to rewrite this equation into L of u equals f given these conditions here. So L of u equals f is equal to L of u is equal to f here. So we have on the left hand side we have u naught when x is equal to 0, because that's what u of x is, 0 here. And then we have negative u double prime for any value between 0 and 1, but not including the endpoints. And then u of 1 when x is equal to 1. That's because it's u of x. Alright. Now, on the right hand side, we have alpha and beta, right? For when x is equal to 0 and when x is equal to 1. And then we have f of x. But I'm going to rewrite this by the given as sine x squared. So, now that we've done this, and earlier in the video I proved linearity, L is linear, we can check mark that off. Alright. Now the second thing we have to prove is that L is inverse monotonic. So we have L of u is bigger than or equal to 0, implies that u is bigger than or equal to 0. Alright, now this is for all x that exists between 0 and 1. Okay, so since we're going to state that L of u is bigger than or equal to 0, right, this implies that u of 0 is bigger than or equal to 0, negative u double prime is bigger than or equal to 0, and u of 1 is bigger than or equal to 0. So, how do we prove this? It's kind of a simple proof, kind of a dumb one actually. But let's say we introduce an arbitrary arbitrary point S, right, such that U of S achieves a local minimum that is negative, right? It's less than 0, okay? Which is contradiction to this one, right? But we're just gonna show that if it didn't, right, it would have this. Now we know from calculus that it would look something kind of like this, all right? Where your x is here, this will be your U of S, S function here. Now, by this graph, we can see that our U prime of S is going to be equal to 0, right? This is the tangent line at that point, is 0. And then we have U double prime of S is going to be greater than 0 because it's concave up. That's kind of a visual proof from calculus. All right. But if U double prime of S is bigger than 0, that would imply negative U double prime of S is less than 0, which contradicts that negative U double prime is bigger than 0, which is here. Alright. So, therefore, we know that L of U of X is bigger than or equal to 0, which implies U of X is bigger than or equal to 0 for all X that exists between 0 and 1. That is, in a nutshell, inverse monotone. But there's a third part that we have to do. And the third part is that we have to show that L of phi of X is bigger than or equal to 1 for X exists between 0 and 1. And phi has to be non-negative and bounded. Forgive my handwriting, I'm speed writing. So let's start with a basic polynomial for phi. We have to build phi on our own. There's not really any help, right? But since we're dealing with double prime, right, or a second derivative, let's do a polynomial with the power of 2, right? That way, at least it exists. Okay. Now, we're going to have to build our phi of x, our L of phi of x, to look similar to what was before. So we're going to have phi of 0 is going to be c, and then we're going to have negative phi double prime of x is going to be equal to negative 2a, and then phi of 1 is going to be equal to a plus b plus c, right? Because I'm plugging in 0 here for this one, and that cancels out these two terms, and then I take the second derivative and add a negative symbol, that becomes negative 2a. Phi of 1 is just 1, a plus b plus c. Okay. So, this is for when x equals 0. This is for less than x less than 1. This is for when x is equal to 1. Alright. So, how do I say this? Since phi of x has to be bigger than or equal to 1, we need a plus b plus c to be equal to 1, right? And in a sense, we need negative 2a to be greater than 0 but less than 1, or equal to. Greater than 0 actually needs to be negative 2a needs to be greater than or equal to 1, which implies that a is equal to negative 1/2. Alright, so we can plug that back in So we get negative 1/2 plus b plus c equals 1, which implies that b plus c is equal to 3/2. Now an easy way to do this would just be look at it and just rewrite this as 1/2 plus 1, right? And then just let that be the corresponding values for b and c. So b is equal to 1/2 and c is equal to 1. This gives our phi of x equation to be negative 1/2 x squared plus 1/2 x plus 1, which can be rewritten as 1 plus 1/2 x times 1 minus x. Now, coincidentally, this is kind of where we should have started from, given the end conditions, because when x is equal to 1, this part phi goes to 0. Phi goes to 1. And when x is equal to 0, this includes that phi is still equal to 1. And anything bound between 0 less than x less than 1 implies that phi of x is greater than or equal to 1 by addition of non-negative numbers. Alright, so we've covered a whole bunch, okay? But we have our non-negative phi. We have to show that this is bounded now. So let's see. Show that it's bounded. Let's just say that we're going to introduce a new variable, right? V of x. And we're going to say this is equal to, we have to prove that this is bounded, so we have to introduce a new variable, v of x, which is u of x plus some epsilon neighborhood times phi of x. Alright, now, since it's linear, we get v of x is equal to L of u of x plus epsilon. Alright. We could write it as this, but that part just goes to 1. Okay. So, we just proved that L of u of x is bigger than or equal to 0, right? Which implies that u of x is bigger than or equal to 0. Okay. And thus, we can use this to say that L of v of x is equal to L of u of x plus epsilon, implies that L of v of x is bigger than or equal to 0, which implies that L of u of x plus epsilon is bigger than or equal to 0. And we know that v of x is bigger than or equal to epsilon, which is bigger than 0. And we also know that, so we can rewrite this by this equation, equation 1, that u of x plus epsilon is bigger than or equal to 0. Going kind of crooked. Is u of x is bigger than or equal to epsilon, which is bigger than 0, which implies that u of x is bigger than or equal to 0. Kind of a weird way to prove it, but this just kind of finalizes that u of x is bigger than or equal to 0, but this doesn't necessarily prove that phi is bounded. So we know that the max of u is going to be equal to c times the maximum of f. And c is going to be equal to the maximum of x exists between 0 and 1 of phi of x, which in this case is x when x is equal to 1/2, which implies that phi of x, or phi of 1/2, is equal to 9/8. Alright, so we get 9/8 times of f. And since f, right, is equal to the maximum value of 2, maximum value of sine x squared, and maximum value of 3, which implies that 3 is equal to our maximum for is our chosen one. So we had 9/8 times 3 is equal to max of u, which implies that max of u is equal to 27/8, thus finalizing the proof. So yeah, it's kind of a tough problem, but it's going to get more interesting when you have to use beta inverses in order to actually solve equations, and that's a very rigorous proof to show that something is well posed. But the strength for well posed, right? Strength for well posed PDEs have unique solutions. That is what it's trying to say. If you could prove through this theoretical concept that your PDE and boundary conditions, the set is well posed, then there's a unique solution and it exists. Alright, so that's pretty much the end of this video. Thanks for watching. Catch y'all next time.